Okay, so for the first part of this homework, we need to describe why the error bar must be perpendicular to the vector that we're trying to calculate. Moving forward, so say we have this green vector that's going out from that point. We'll call this V. We have this smaller vector right beneath it, vector, and we have our error approximation coming down from there. So we need to explain why the angle between this u vector and v vector needs to be at 90 degrees. So if we write this out, we can say that, E is slightly, is equal to, not slightly equal to u. Now you might be wondering to yourself, oh man, what's this C1 value? This is how many u vectors it takes to get to this point right there. So that's very important to know. So in light of this kind of equation, we need to determine this proof. This will help us later on in the video. So it's the u vector times vector is equal to 0. This proves that we need to have this equal 90-degree angle. You might be asking, why? Why does this matter? Because when you take the dot product of two vectors, it's really the absolute value of this vector times the absolute value of the other vector times the angle between the two vectors, right? If this cosine was anything other than 90, this would be false, meaning that our error approximation would be all cattywampus, going there, maybe even there, but it would not line up straight. So having it be a 90-degree angle gets us to that point, and that's true. So now we can get into the matrix vector equation for multilinear regression. Let's say we live on a 3D plane, or we have a vector on this 3D plane. So we have our z-axis, these straight lines. Directly through it, we have an x, a y, and a z axis. So let's say we have this blue vector shooting off over here, or this v vector. Sorry. We want to approximate this u vector, or this v vector, with two other vectors in there. So we'll call this theta, maybe it's on the xy plane. Oh, and that one, theta 2, is on the zy plane. Now we have these two vectors, and we want to create an error kind of bar, like we did for the first problem. So we'll make that yellow. Say that's E. Know that the v vector, right, equivalent to u1 or c theta 1 plus c2 theta 2. So we can say that this is true. Then inversely, we can determine our error vector minus c1. Then we can rewrite that as a summation if we really, really wanted to. But one of the things that we can do now is rewrite this, because this is true, same equation. But instead of the u, we have now our theta. So let's get this in a different color. So now we have theta 1 plus, or theta 1 dot product, our error is equal to 0. Theta 2 dot product, our error is also 0. Because we need to get it to 0, because it has to be perpendicular, like we mentioned earlier. So this gets us to this kind of equation where we can rewrite that and place it in for the error, but we can make it a generalized equation. So we can make this a J. So we have C1 theta plus C2 theta 2 dot product theta J to our V vector theta J. Right? Dot product. So this can get us pretty far for designing this matrix. So where we can go past this point is kind of get this into a matrix format, right? So let's say our V vector is 100 values of just random numbers. So it's a vertical. It's vertical. That's what we want to clarify. And so are these. These are vertical values too. All vertical. So the issue is that we have two unknowns and then these long, very long columns. What we can do is transpose one of these vectors, which essentially knocks it over. So we go from a very tall vector to a really wide vector. That's going to help us a lot. So let's do that for this J vector. So where does that get us? So now we have this theta 1 vector times theta 1 bam, 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 theta 2 bam, 2 all over or multiplied by the V vector bam bam, which is still horizontal, times this long vector here. So this is something. This is only for theta 1. But we still have this theta 2 up here that we haven't really dealt with yet. So what we can do is, instead of rewriting this whole entire thing, we can add theta 2 directly into these spots, right? So let's do that. Let's erase these yellow marks. Bam, bam, bam. And then just add theta 2. So this gets us nice, neat boxes. So this gives us a 2x2 matrix. We'll write this in green because we go from 2 columns, or 2 rows, 2 columns, and then one column, or a bunch of rows by 2 columns, 1 column. You get the picture. So it's a 2x2 matrix. Bam, 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 bam. 2x1 matrix. Bam. Get a 2x1. Bam. Bam. So this is it. It doesn't look like the matrix vector equation, but when you simplify it, you have this design matrix right here, right under your nose. Which makes these design matrix transposed. E represents it being transposed. So you have, your y, you have some constants, a, t, y, a. There it is. That is your matrix vector equation for multi. All right. So right now we have to kind of fit this Antoine equation to the multilinear regression kind of design matrix that we just made. So we have the Antoine equation right here, right? Log P is equal to A minus B over TC. So let's change this a little bit. So we can get TC over on one side, multiply it by log P is equal to A TC, right? Minus B. So let's kind of expand it out correctly. So T log P plus C log P is equal to AT plus AC minus B. So in general, or in the final kind of cut of this equation, we get AT plus AC minus B minus C log P is equal to T log P. So there are a few variables that we can get in with this. So we can get, what was it? So the equation we can pull from this, we can make D is equal to AC minus B. And then inversely, B is equal to AC plus D, but that's for a different story. So we can get our design matrix and our matrix vector equation kind of from this equation right here if we substitute in D. So we have AT plus D minus C log P is equal to T log P. So if we get the matrix out, let's make this a different color. Let's do a nice blue. I like blue. So we get T1, T2, so on till Tn log P1 log P2 log Pn, and then just a value of 1s. And then we have our three constants that we denoted, A, D, and C, right here, right? A, D, C. So the reason why we can kind of do it like this is because, or why we can have that D component in there is because they're just numbers. They're constants, or they don't change with temperature or pressure. So that's why we're able to just have those as constants. And then we have on our final side, T log P. Let me 1 T2 log P2, and you kind of get the idea, Tn log Pn. So like this, we can multiply, we could do the same thing as we did in part 1, where we have our design matrix, and we have our Y, we have A, we have T. So we can multiply our design matrix, which is this component right here, A double bar, by the transpose, so we can get get a 3x3 kind of equation out there. So that's very cool, and that's what we need to do. So let's move on to the coding aspect of this problem. All right, so let me put the iPad to the side, and let's get started. So I already went ahead and got the raw data file from Carlos's GitHub. So we have it in there, and it's in this console right now. So the first thing we need to do is import numpy as np, and then also we need to from plotly underscore subplots, dot subplots. What do we do? import make subplots. Awesome. So now we have to do we'll name it RW is equal to np.load text water vapor pressure. Is that the name of the file? Yeah. CSV. And then the delimiter is that. And then we have to make some matrices. So we have T data, and then P data is equal to the raw RW dot T data. Awesome. Why is it line 10, 12? That's very odd. So now we're at the next step where we have to kind of make the previous equation that we found into kind of collaboratory, the first kind of design matrix. So that's our temperature data, and then our negative log P data, and then just a row columns of 1. So let's do that. Let's do DS for design matrix is np np.c underscore t data, not data, negative log, np.log np.log p data, comma np ones underscore like t data. Class negative. Did I mess up? Oh, there we go. Awesome. So how do we move forward? So now we have to get our second column, the A, C, and D column. So A, C, and D column are equal to the np.linalg.solve. Then we have our DS matrix ds.t, ds.t matrix at our M matrix, because what we're doing here, or here, is the we're doing the transposed, and that's why we have the dot T. So used to typing M's. So now we need to multiply our temperature and log pressure matrix by the transposed of our design matrix. So we have ds.t multiplied by our T data times our np.log p data. So that's living La Vida Loca at that rate. Should be good. Yeah. Cool. And then we need to set B is equal to AC A times C plus D. Yeah. So now time to make a big old plot. So we'll name plot t is equal to np.len space t data dot min comma p data dot max comma 100, because we want to have, let's say, 100 data points, right? So we have fig is equal to make underscore subplots, and then what? So now we need to add our actual data points in there. So we do fig dot add underscore scatter. X is equal to t data, y is equal to p data, and then mode to markers. I like it. I like it. Doesn't look right. Oh, supposed to be T. There it goes. Okay, let's continue on. So now we need to add in the actual Antoine's equation. So fig dot add scatter, x is still equal to t data, y is then equal to the actual Antoine's equation, but we have to move the natural log over to the other side. So this is really to the np.exp, right? And then it's a minus, what was it? B over plot E plus C mode maybe I have to but these might be getting confused. Whoopsies. What's happening? I'll be right back. I see the issue. It needs to be there. Now, that does not look right. Moving on. So, fig dot add underscore scatter Why is this bad? Ooh, that's minus D. In marker T data. That's correct. Where's my data bad? Be right back. I found my issue is that this needs to be the plot T There it is. That's our data. And that is fitting the Antoine equation to a multilinear regression matrix vector equation. Sorry for the delays. All right, so let's say you have this hypothetical set of data. All right, it lies on the XY plane. You have it's just all over the place. It's all over there. You can make this model that kind of fits the data pretty well, or in some cases, it's close enough for it to be all right. We'll call this Y model equal to mx plus b. So with this, there are certain variables that we need to really get to on that. So we do the sum of least squares. Sum of squares, which is equal to the sum, surprised, n I is equal to 1 of mxi plus b minus y. So one of the things about this is that you could use one of the things is you have error in this, right? It's not always going to be positive. Sometimes you'll have negative error. So what you have to determine kind of is whether you want to use the square root or the absolute value. However, the only real answer is using the square root, and that's because when you have the absolute value, say we have, this plane, and then, the absolute value of your error is that the derivative of the absolute value can either be, positive or negative. So you can't really justify doing that. So you have to use the square. So in our case, we must square this answer. So knowing that we must square our answer, we could then take the derivative of this with respect to x and get 2 summation mxi plus b minus y x I is equal to 0. So how can we move on from here? Well, we can distribute this x out to all of our terms. So that can get us to 2 m sum x I squared plus b sum xi, and then we'll just move the yi over, right? Xi, yi. So we have this equation, right? Now, how can we go on from here? Well, we can change this variable to just be yi because x times y is just going to be a number. It's not dependent on anything. No matter where it lines up with each other, right? You're not going to have a different xi value for a different y value. It's always going to be the same, right? So it doesn't matter what it is. Now, if this was, xj, you couldn't do that, but it's xi. So knowing that it's just xi, we can start to build this design matrix that we want to have, like we did for the first one. So we have 2 constants, right? We have m and b. We have that. So, or not that, my bad. So we have m and b, bam, bam, and then we just have these values of xi, bam, bam, and then 1s. And on the other side, we just have a column of yi. So we get to some arbitrary value or where our data finally ends. Now, the issue is that this does not line up with this, right? We need to multiply our design matrix, which again, we've made, right? It's right here. This is our design matrix. So we'll write that out. A double bar is equal to design matrix. We need to multiply these by our design matrix. So we transpose it, so we would see I, right, then just a bunch of ones. So this is finally at a point where we can start working with it. So we have our A, our constant, A transposed equal to our Y times our A transposed. So we've kind of proven that through the least sum squared, we can finally get to the same kind of design matrix. So one thing I wanted to come back and say that this is the sum squared error. Sum squared error. So we can visually see that this equation m sum xi squared plus, we can actually rewrite this middle term as b sum n is equal to yi, because this constants are not constant, but they change. We actually get our design matrix, which matches up perfectly with this one, right? Because once we do the matrix math of it all, we get a 2 by whatever, multiply a whatever by 2, that's 2 by 2, by a 2 by 1, and that gets us a 2 by 1. Again, at the very end, or a 2 by whatever, which works out perfectly for our kind of problem.